Let's take a look at the idea of partial derivatives. Now consider, first of all, this table, which consists of the National Weather Service wind chill chart, where the actual wind chill is a function of both temperature, the outside temperature, and the velocity, or actually the speed of the wind. So suppose we fix the temperature at 20 degrees. If I fix temperature at 20 degrees, what that's actually saying is I'm looking at this column right here. So if I'm looking at that column, we can now take a look at how the wind chill changes as a function of the single variable, simply speed, because speed is over here. We can now talk about the idea of the temperature, actually the wind chill, as the velocity of the wind perhaps approaches 10 miles per hour, given or fixing the outside temperature at 20 miles per hour, or 20 degrees. So I think we can easily see that as we approach 10 miles an hour from below or above, the wind chill factor is approaching that of 9 degrees. But remember, the idea of a derivative is that of the rate of change. So what's the rate of change in wind chill as the outside wind speed approaches 10 miles per hour, given that the outside temperature is fixed at 20 degrees? What's actually the meaning of that? Well, on a table like this, we can't just take the derivative of the function in the way that we've come to love and adore, but we can approximate it quite well by looking what happens to the function. And this is a function, it's a tabular function, as we're above and below, approaching the specific value that we're interested in. Now, if we could simply take the derivative as such, then the derivative of f specifically when v equals 10 is the rate of change of wind chill with respect to wind speed. Whoops. Specifically when that wind speed v is 10 miles per hour. Now, in terms of a function, the way we would think about this is we'd say, gosh, that f prime evaluated at 10, using the basic definition of a derivative, equals a limit as h goes to 0 of f of 10 plus h minus f of 10 divided by h. But remember, this is actually, f is a function of two variables. So this is really equal to the limit as h goes to 0 of f of 10 plus h comma 20, there's my outside temperature that I fixed, minus f of 10, 20 divided by h. But like I said, we don't actually have this function to work with in terms of a continuous function to use the laws and properties of derivatives that we've come to love and adore to find that derivative. So what we can do instead is we can actually do a pretty decent job of approximating this derivative by using values above and below. And in this case, I go plus and minus 5 miles per hour because the table actually works in terms of 5 miles per hour. So I can say that f10, or f prime of 10, the derivative at 10 miles per hour, is approximately equal to f of 10 plus 5, see now my h is plus 5, comma 20, minus f of 10, 20, over, well, h is 5, and that's going to be, see, 6 minus 9 over 5, which equals negative 3/5. Now these values, 6 and 9, came directly from the table. At h is 5, I'm actually at a speed of 15, and there it is. It's at 6 miles per hour. And then obviously f of 10 is at 9 miles per hour. Or wind chill is 9. I'm sorry, I said miles per hour. I meant actually wind chill value. So likewise, I can say that f prime at 10 is approximately equal to f of 10 minus 5, 20, minus f of 10, 20, over a negative 5. And that, you're going to see, is 13 minus 9 directly off the table, divided by a negative 5, which is negative 4/5. See, now that I've got these values, these approximations going above and below by 5 miles per hour, and again, the reason I chose 5 miles per hour is simply because that's what the table goes by. It goes by increments of 5. I can take the average. So if I average these, it's going to be negative 3/5 plus a negative 4/5 divided by 2. And what I'm going to end up with is a negative 7/10. What this means is if the outside temp is 20 degrees, remember we fixed it at 20 degrees, and the wind speed is 10 miles per hour, then the wind chill drops approximately 0.7 degrees for every mile per hour increase in wind speed. It's really the same way you would typically interpret any type of derivative. But we approximate it, like I said, by going above and below because we have a table to work with. Now, likewise, we could fix a value of the speed. And if we do that, we could then look at the change in the wind chill as a function of temperature with speed fixed. Now, this whole idea of fixing one of the variables at a specific value and then take and look to see what happens with respect to the other variable in terms of the derivative is the whole concept behind the idea of a partial derivative. What we did up here, when I found this is really estimating the partial derivative for wind chill with respect to wind velocity, fixing a specific value of the outside temperature.